This is a small presentation of the paper Automated Deep Learning for Load Forecasting. This paper explains how we successfully applied automated deep learning to find performing neural networks for the load forecasting task, outperforming the industrial models and other AutoDL frameworks. This work has been funded by Électricité de France, or EDF, which is the main electricity producer in France. The load forecasting is crucial to this company. Indeed, electricity storage is inefficient and expensive. To ensure the stability of the grid, it is essential to have a strict balance between load production and consumption. This balance is maintained by first forecasting the load production and the renewable production, and then by adjusting the production of programmable power plants such as hydro or nuclear in France. These forecasts are becoming even more important with the increasing share of renewables, creating more uncertainties on the supply side. If the balance is not maintained between EDF's clients' consumption and its production, the company can get penalties of hundreds millions of euros. The load signal can be seen as the sum of several explanatory variables. Therefore, regression models are performing way better than time series models to forecast the load consumption. In the industry, the regression models are trained only with the explanatory variables for data streams availability and explicability reasons. They can then be recalibrated with past load data using online learning. The scope of this paper is only about regression model, and we don't tackle the online learning part. The state-of-the-art forecasting models are generalized additive models, which are kind of generalized multilinear regression models. They are used in the industry and they win load forecasting competition. To improve the performance of these models and to respond to new industrial challenges such as the integration of new data, the forecast at increasingly finer steps, interest in the community is growing into deep neural networks. However, using neural networks for load forecasting is not an easy task. First, there exist no reference models for regression tasks such as transformer in NLP or convolution in computer vision. Moreover, the DNNs used in the literature for load forecasting are based on models adapted to time series forecasting such as recurrent neural network or LSTM. They perform rather poorly on our industrial use case. In our search for new models, we turn ourselves to automated deep learning, also called AutoDL, in order to discover new architecture that could match or even beat the state-of-the-art regression models for load forecasting. We ended up creating Energy Dragon, an optimization framework that is able to automatically find DNNs, outperforming the state-of-the-art for load forecasting and other AutoML tools. Energy Dragon is built upon the framework called Dragon for Directed Acyclic Graphs Optimization, which is an optimization framework to search for performing DNNs for any task. Dragon has been implemented as an open-source Python package. In Dragon, the DNNs are represented using directed acyclic graphs, also called DAGs, where the nodes are the layers, for example, convolution or pooling layers, and the edges are the connections between those layers. They are encoded within the package using their adjacency matrix. Finally, each node, L1 to L4 in the slide, is encoded as a combiner followed by an operation parameterized by a set of hyperparameters, the convolution or the recurrence, for example, and an activation function. There is indeed no constraint on the number of incoming edges for each node. Therefore, the combiner is necessary to combine the arbitrary number of entries. To modify those directed acyclic graphs and to look for optimal configuration, Dragon is offering some search operators. It is possible, for example, to add a node or delete a node. We can also modify the outgoing and incoming connection, and we can also change the node's content. The search operators are then used for different search algorithms. In our case, we choose the steady-state evolutionary algorithm implemented on HPC. An iteration of this algorithm starts with an already evaluated population. Here the best model is the yellow one because it reached a loss of 0.1. Then, if a process is free, it may select two DNNs from the search base, evolve them using the search operators, and then train them. In the meanwhile, another process might be free and perform the same operation. Once the training and evaluation are done, the models better than the worst one from the population replace them. Here, 0.5 is lower than 1, the loss of the red model. So our new model can replace the red one. Upon the Dragon framework, we added a feature selection layer, which is crucial in load forecasting because of the large number of potential explanatory features. Each feature is associated within the neural network to a probability of being chosen. Those probabilities are optimized during the training alongside the model's weights. At the end of the training, if the probability is close to 1, the variable is selected. If it is close to 0, the variable is not selected. The use case considered in the paper is the daily forecast of the aggregated load of a country or a region. The input contains the daily explanatory variables and is of size h times f, where h is the number of time steps within a day, for example, it might be 24 for holiday forecasts, and f is the number of explanatory variables. The output is the aggregated load signal of dimension h. The neural network should then convert a two-dimensional data with two-dimensional operation towards a one-dimensional data. Therefore, we use two Dragon DAGs, the first one handling two-dimensional data with two-dimensional operations, and the second one handling one-dimensional data with one-dimensional operations. Our objective function is the map, and we use several such algorithms, each of them having a time budget of 24 hours. We compared a random search with the evolutionary algorithm with and without the crossover. The experiments were done on the national French load consumption. The paper also contains an annex on the national Norwegian load. The baseline is made of models used in the industry, for instance a GAM and a handcrafted neural network based on CNN and MLP layers. This neural network is also used in the initial population of some version of Energy Dragon. We also added an open source baseline containing AutoML frameworks such as AutoPytorch with and without the optimization of traditional regressors such as CatBoost or Random Forest, and also a version of DARTS applied to the architecture of the handcrafted model. These are the results on the French use case. We implemented 5 versions of Energy Dragon with various versions of search algorithm. For instance, we used a random search, a steady-state evolutionary algorithm without the crossover, a steady-state version of the evolutionary algorithm with the crossover, and both versions of the steady-state evolutionary algorithm with the handcrafted neural network called CNN-MLP in the initial population. All versions of Energy Dragon managed to beat the GAM model, which is our baseline. No other model from the baseline, for instance AutoPytorch with the traditional baseline, the handcrafted DNN, and DARTS, were able to do so. The best algorithm is the evolutionary algorithm without the crossover, but with the handcrafted neural network in the input, and this version improved by 20% the result from the GAM. Here is displayed the forecast of the best model on the last week of November 2019, again the ground truth and the forecast of the GAM. We can see that the GAM is overpredicted compared to Energy Dragon. On the left is represented the best model found by the random search. This model is very small and only has 3 layers. On the right, we have the best model found on this dataset by Energy Dragon. The first tag is only made of 2 layers, but the second one is much more complicated. All versions of Energy Dragon were run on 20 GPUs V100 for 24 hours. We have here the loss of the best model found through time for each version of Energy Dragon. The GAM performance was around 1.4 of map, so each algorithm here will manage to beat this baseline within 4 hours of running. This is all for this video. Thank you for listening to it. Do not hesitate to read the paper for more information.